Let's design a very simple cache architecture. Let's start with a very simple index memory. It has space for storing 4 data items. Now let's also assume that the address space also has only 4 addresses. So now I can map those 4 addresses as follows: 0, 1, 2, 3. And now given an address, I can use a simple decoder to select one of these 4 locations and retrieve my data. Now let's make it a little bit more complicated. Instead of 4 address locations, I'm going to assume that my program can access 32 address locations. But my memory has only 4 data items, space for 4 data items. So now I have to treat this like a cache. Now the question is how to map the 32 addresses to 4 locations. And how do I know which of these 32 locations I have cached? To solve this problem, we need one more array. Okay, now I have created one more array. I'm going to call that as a tag array. The original memory, I'm going to call that as a data array. Even though I'm going to call them as arrays, these are hardware structures. Now, when I cache address, I can note down the address location in my tag array. So let's say I access the location 31. I note down the address and then store the data corresponding to that address in the tag array, in the data array. And I can continue this process. Let's say I access an address 10, then 20, and then let's say 0. I would have their corresponding data in my data array. And let's say I have a address that I want to access. Let's say the address is 10. How do I know which row contains my data? Well, I need to take this address and compare that address to each of these tags. If the tag matches the given address, then I know that I found the data that I was looking for. Now this is what we're going to refer to as a cache hit. I was able to find the data of an address that I was looking for. Now the question is, what type of a hardware structure would allow us to perform so many comparisons in parallel? So this hardware structure that supports this functionality is called the content addressable memory, or shortly CAM. CAM is a very simple structure. It has the ability to store a set of data items, and given a key, it would compare to all the data items and then tell us whether it found a match or not, and if so, which entry found a match, which is exactly what we explained as a tag array. So the hardware for CAM looks something like what I have shown in the picture here. You have the key that is given as search data at the bottom, and you have the data items, or in our case it would be the tags that are stored in each of these rows. So in order to perform a comparison in parallel to all of these rows, I would drive these vertical lines that you see in the picture with the bits in the search key. And the little dots that you see here are the ones that implement the comparison functionality, in the sense that if the given bit matches with that of the stored bit, it would raise the signal in the line that is connected to it. And the end result is that if all of the bits that are stored in a given row matches with that of the given bits in the key, then that entry would be enabled. And that's how we can discover which entry contains the data that matches the key that is given. So we have used CAM in the past. So if you go back to our data path with the branch predictor, so think about the branch target buffer. So if you recollect, a branch target buffer is one that stores the program counter of the branches. And when you see a new branch, you take the program counter value, and then you want to search all the entries in the branch target buffer and see if that branch exists in the branch target buffer. And if it does, then you fetch the target, and if your predictor says taken, then you jump to that target. So the structure that we would use to implement a branch target buffer is also a CAM. Now let's get back to our cache design. So we have two arrays, tag array and a data array. The tag array is implemented using CAM. Now let's briefly understand how this cache would work. If I provide an address, let's say 10, I would first look up the CAM and see which entry matches. And there would be no more than one entry that would match. And then I would know the entry in the data array that I should be accessing. And so then I would retrieve the data and then send that data back to the processor so that a load or a store can use that information. Now let's say instead of 10, I provide an address, let's say 7. You would again look up the tag array, and you will discover that 7 is not present in any of the rows. Now that would be called a cache miss. In the case of a cache miss, you wouldn't find the data for the address that you're looking for, and therefore you would have to go to the next level of the memory hierarchy, typically the main memory. Now when you do go to the main memory, you would fetch the data corresponding to the address 7, and you would want to bring it back into the processor and store it in your cache. But we have a problem. Our cache is already full, and so there is no place for another data item. So therefore we have to pick a victim and evict the address that is chosen as a victim out of the cache and replace that with the new address 7. We have, obviously in this example, we have 4 choices. Now the question is, out of these 4, which one would you select as a victim? Now that is informed by what's called as a replacement policy of the cache. So the question is, how do I design my replacement policy? To understand that, we have to understand a concept called temporal locality.